LTSpice. Why PSpice specifically?
Okay. So our main aim would be not to simulate the circuit. We will do a complete board design. Okay. So let us say we had yesterday some problem. Like problem statement was we have a project which requires we have input voltage to be 24 volt and output voltage rails are 5 volt 200 milliampere and 3.3 volt 300 milliampere. So all these put together, you may not be able to put lot of circuits in a simulation file. Okay. So we are going to learn one software which is actually OrCAD. This is a licensed version software which is utilized in many industries. There are other also like LTM and all. But I will be teaching you guys one of the software which actually, the industry demands. As a professional, you must have one knowledge of circuit entry. So I'm going to teach you a circuit entry tool. I'm not going to teach you the simulation. Okay. Now one more thing is PSpice for TI is actually equivalent to OrCAD. So OrCAD has PSpice and PSpice, same PSpice is there, which is like taken by Texas Instruments. Okay. So this software gives you a provision of utilizing lot of circuits. Let me give you an example. Let's say if you have to develop a very big circuit of, let's say, how many pages, like some 13 page or 12 pages. So this will not be possible to design in LTSpice. Okay. Very big circuits, right? So you won't be able to produce this. This is just an example. I'm not telling you that this is the only circuit you have to design, but there are a lot of circuits you have to put that, like microcontroller, FPGA, all those things. So for that purpose, we are going to use PSpice for TI, which will actually look like OrCAD. And you have a skill of OrCAD development as well. And this is a very great, like skills to have for any electronics designer. So actually PSpice for TI looks like this. I am going to close this software right now. Okay. So any project open, I'll just close it. Now, my screen is, very blank. Now what will happen is you just have to type in start PSpice for TI. Okay. So PSpice for TI, if it is installed in your software, have a close look on this because I'm going to explain you very nicely from beginning to end so that you can have a very good understanding about how to develop a circuit. Okay. Same thing will happen in OrCAD, like you have to type OrCAD capture and it will open. All right. All right. So this has opened up. I'll just like close some files so that it can be a little faster. Okay, it tells you that apply latest library, update library. If you want, you can update it. I will not want it, so I have closed it. Okay. Now, once this opens up, what you have to do is you have two things. Either you can press on new or you can go to file and new. New project will come. Okay. So you can press any place, not a problem at all. So let us start to create a new project. Okay. So press on this new project name you have to give the project name without a space. Okay. And select a location by browsing it. All right. So what we will do is we will close this. We'll go to file, new project. So anything is fine. So both the things will be same. So let us say hardware design test. So I have written a project name hardware design test, and I can, like give the location. Let us say I've given here VIT University, let it be there only. Okay. Or if you want, you can browse this by 3 buttons and it will tell you like what it is. All right. So let me, design here materials, sessions, and I'll just put it OrCAD files. So this is the place I am going to put the file and put select folder. So you have this particular location. So you have to give a name, then you have to select your location. Try to put a location inside a folder so that all the files that will be generated will be inside one folder. Okay. Otherwise, it will be very misconfusion. Like you have bill of material, PRJ file, test file, simulation file, lot of files will be there. So you have to keep inside a folder so that you do not miss it. Okay. How it will look like, I'll just show it to you. So once you go inside, you have sessions, you have OrCAD files. Okay. So in this OrCAD file, these many folders and files have been created. So there are two files that you have to take care of always. One is .opj file. This is called as project file. Okay. And this is DSN file. So DSN file is the one which will be keeping all the circuits that you are going to design. So its size will be keep on increasing as you start keeping, putting the circuits. That's the understanding you should have. So .dsn file is the one which is having the schematic file. Now, very first thing that you have to do is if you want, you can, set your window by dragging little smaller and let's say little bigger so that all the project tree and everything is visible properly. Okay. Now this plus sign tells you this is my project name, hardware design test.dsn, and you have to just double click here or click it there. It will be having schematic and design catching. Let us talk about schematic. If you want, you can right click on the schematic and change the name. Okay, rename. So how to do that? Like schematic, right click, change the name. So rename, it will ask you to put the name. I'm not going to change it. By default, one page will be added to the schematic. If you want, you can add multiple pages. New page, page 2, new page, page 3, like that. Okay. If you want, you can add schematics also, like right click it, new schematic. So what you have to do is .dsn file is the root file, right click it, new schematic. So new schematic, schematic 2. The schematic 2, there is no page by default right now. Here you have to insert a page. So right click it, page. Understood? So this is how multiple schematics are entered, multiple pages are inserted. Okay. Now, let me just delete this. I don't want this one. And page 2 also I don't want. Okay. Now, let us do one thing. Very first step towards the designing of a circuit is keeping your title block of your company. Okay. So they will tell you like which title block will be coming. I have kept by default whichever it is coming from the OrCAD. Okay. Now, right click the page 1 and you have schematic page properties. If you want, you can rename the page also, like it is MCU circuit or some other circuit. So that those things you can do. But what I'll do is I'll go and page properties. You have different size of pages like inches, A, B, C, D, all these inches are there. E is the maximum size. Custom is also there. If you can click custom and give your own size. So it's up to you like what you are going to give. Now I will take millimeters. So I always prefer, let's say A3 size for, like FPGA or microcontroller circuits, and rest other circuits, I'll try to keep A4 size so that A4 size looks little bigger. Okay. Like font size and all, I want little bigger. That's why. So millimeter A4 size. Got it? Press OK. It will automatically take this A4 size of this circuit. So right now it is 246 by something. It will become little bigger. Understood? So size we have set. Now, whichever component you will place inside this, all these components will be listed towards the design cache. Okay. So you don't need to have the library to send your file. All the libraries components will be actually included in the circuit itself. All right. Now other parts, if you see, like you have the menus, very simple. Like as we proceed, we will talk about them. We have parts placement. We have this part placement, like part placement, you can do that. But one by one we'll do. Don't worry right now. Now, next thing what I'm going to do is, before designing a circuit, if you want to be a, like inside a company, this simulation and all doesn't work. You have to be a very skilled professional. Okay. So in that case, just try to have this kind of understanding first. Okay. A very basic components that you need to have inside your circuit library. So what are those components? You need to have resistors. So have all the common packages, like let us say 0402, 0603, 0805, or 1206. All these kind of packages you try to keep. Okay. Then capacitors also you keep. Let's say 0402, 0603, and 0, all these things. Okay. And then you can keep like 1210 also, and many other packages are there that I have taught you while selecting the resistors and capacitors. Okay. Keep few more components like connectors. It can be of like 2-pin, 3-pin, or 4-pin. 4-pin can be of 2 rows also sometime, or single row, or 6-pin. So all these things, even 16-pin. So all these connectors you try to keep a very basic. How to create those components, I will tell you. Okay. And these days many industries are coming up with their own spice file or component files that you can directly import here. Okay. Similar to that, we have fuse. Fuse will be generally like this symbol. Okay. Then what we have, like let us say inductor. Inductor will be like this. Okay. So it's up to you, like how do you, like represent, but basically try to, like be professional and keep the standard types of components. Okay. Now let us open my OrCAD. So I'll tell this as OrCAD because we are actually working on OrCAD. The OrCAD window also looks exactly same. Few of the options will be disabled here because let us say if you want to have some tools here, netlist is not there. See, they are, like grayed up. So all those info, like options, it will not be possible, but you will be able to make as many circuits as possible. Okay, whatever you want, you can do that. So first job would be, there are few components that is already there in the software. So you can go to place. Place is the place where you will find all the components like wires, auto wires, bus, junction, power symbols, ground symbols, off-page connector, hierarchical blocks, okay, all those things. And if you want to place some rectangle, line, or text, or arc, or ellipse, whatever you want to put, this place will give you all those options. Now, if we want to place the parts, that is here from your libraries. Otherwise, PSpice component is also there, which is a simulated file. Okay, so there capacitor, inductor, all these things are available already. So let us say capacitor I will put. So capacitor will come. So unless you press either right click or escape. If you press escape, it will go away. Or if you press right click, it will go away. Until the time, it will remain as it is. Okay. So how many number of components you want to place? You have to press left click. Okay. So left click to place the component and right click to escape this command. So I'm going to put right click, it will go away. In the mode, something like that. So I'll just escape it. Escape is very easy. If you want to mirror and all, you can do that also. That is not a problem. Rotate and all, that also you can do and place. Some like shortcuts are there, like Control R for rotate. Okay. So Control R you can do, it will keep rotating. So anyway, that is not a problem. I don't want to keep these components. But let me just show you what design cache has done now. I have clicked on design cache and you can see we have C, this has been added and the complete library path is also given. This is analog.olb file. So the libraries that is actually, put inside is called as .olb file. Okay. So any component you make, that will be .olb file. Now let us say you have deleted all these things. So cache has not automatically deleted. If you want, you can clean this up. So go to design cache, right click it, clean up cache. It has removed because the capacitors are not there. So this was all about the inbuilt library in this PSpice that you would like to use. If you want, you can quickly make that. However, I'll share you a file of libraries and you will be able to use them very nicely. And any additional component you would like to make, you have to save as one of the component and create your own library. Because here in library, the OrCAD licensed version, you will be able to add symbol also. Okay, like create a new symbol or something. But here the option is only to add files. So I have already a library. I'll go and add files. Okay. So let me just add files. So see, library one I'm going to add, and if you mouse over, it will tell that this is .olb file. Okay. So this .olb file will be added. Yes, please. Tell me, please. You have any question? Sunil, you have any question? Okay.
No, sir, not yet. Actually, by mistaken. By mistake, this. Yeah.
All right. No problem. So, so what we have to do now is you can like mute yourself. Yeah. So so what we can do is this library file. If you click on this plus symbol, it will tell you what are the different components that is added here. Okay. And you believe it, like the very first thing that I tell any hardware engineer, if they are working with schematic design, try to create all the resistors. So see, resistor, if I type here in the search box, resistor 0402 is coming, 0603, 0805, 01206, all these are there. Okay. Even 2512, 4 array. So all these, just click it, it will come. Okay. So like that. So let us write some resistors. 0603. So this. Okay. Similar to that, capacitor will be there, inductor will be there. Any part you search, it should be there. If it is not there, you can make by yourself. So how to do that? Let us say I am going to work with a regulator, linear regulator. So I'll search that part, which is, what was that? ADPL 42005. So 42005 I have, and the package which I will take is which one? LFCSP package. Okay. So this package I am taking. Okay. So automatically there is a prefix of the like reference designator, like U for ICs, R for resistor, C for capacitor. All these things we follow. Okay. So U1, U2, U3, it will keep on coming. Like if you just go here and place one more, so next time U2 will come, next time U3 will come, like that, it will keep on coming. Okay, that's all. So let us create the actual circuit that we had developed yesterday, and then we will see how to, like generate all the files and all other parts. Now let us say if you want to create a separate symbol for yourself, I'll just take 1 minute time. Let me just do that. This is not there. Let's type down. What is that? ADPL 42005. Yeah. So this is the data sheet that you can see, right? Now you can see the pin numbers are arranged like this: V output, adjustable pin, ground pin, NC pin, all these things, right? But I don't want to create my symbol like this. I want to create my symbol some other way. Like I want to put here input, I want to put here output, I want to put here ground. So like that I can want, and I can, like arrange those pins like that. Understood? So for that purpose only I have done here. You can see input is left side, enable is here only, no kind of grounds are there. Then my power good pin and adjacent pin, all these things are there. Got it? Now let me create that circuit. So to create that circuit, what we need to do? Let us open ADPL circuit that we had studied yesterday. Okay. Now our aim would be to develop this circuit separately and see how it works. Okay. So what we will do? We need to have input capacitors, right? Now this is the challenge for you guys. Like our aim is to convert 5 volt to 3.3 volt. So we have to keep a capacitor of, let's say, 10 microfarad. So what should be the package of 10 microfarad that I can keep? I need to have minimum 16 volt capacitor, because I don't want to go ahead with 10 volt or something, because the biasing makes the capacitor go very down. So I will take 1210 package, okay, capacitor, because it is very high voltage rating. Okay, so I'm going to take one capacitor of, let us say, 10 microfarad. Since these parts, capacitor, inductor, resistors, are not a specific parts, so you can go and change the values on your requirement. But in companies, you will see all these symbols are created based on the manufacturer part number. So those are very specific symbol. But what I have created, if you double click it, you will see the like all the properties. And here you can change your manufacturer name, manufacturer part number, everything you can change. PCB footprint, if you want, you can change it, but better don't change it, so that you have a uniformity. Okay, and the values you can change. So this is how the symbol properties will look like, or parameters will look like. If you want to add some new properties, you can go to new and put some property. Let us say I want to put assembly, like whether I want to assemble it on the PCB or not. Then put assembly, and let's say press DNP, like do not mount or do not populate, and then I will write OK. Now this DNP will not appear here because it has not been displayed. So go here and display property, and in this display, this is selected do not display. How to do that? Go to DNP, then display, and then you have value only, name and values, whatever you want to display, you can do that. So value only I will do. Now the font size, all these things, if you want, you can use default. Color, I will just change it so that it will not be black. I'll just make it, let's say, this color. So if you press OK, that property will be visible there. So whether if you want to save it, that also fine. Doesn't save it, that also fine. It will automatically take that. Okay. So see, this DNP is appearing. So it means like you do not want the PCB guys to, I mean, the assembly guys to, put this component on the PCB. It will be vacant. Got it? So like that it was. So let us delete this, or okay, anyway we'll keep it one. So let us keep that C2, and then and then what is that? Output side also we need same capacitor. So I'll just put 2 capacitor output side also. And then we will take 0.1 microfarad. So let's say 0603 package is enough. So capacitor right side, 1 capacitor I'll take filter capacitor, and 1 left side. That's all. So capacitor is fine. Next is we have to have power and ground. To get the power and ground, where we need to go is go to place, and then we have power and grounds. Okay, so select power, and then here you have VCC like this symbol or this symbol, arrow or bar. So I prefer to have bar. Arrow you take it for locally, but bar is always preferred for me or anybody. Okay, so I have taken bar. Now if you want, you can change this. So let's say I'm going to write down plus 5 volt. If you want, you can create also separately for yourself. Yes, please.
Quick question for me. In regards to the capacitors, are you basing that on the load application current, or you're just choosing based on the datasheet minimum requirement?
No, we will choose based on our load parameters. Minimum requirement data sheet we will not prefer. That will require just 1 microfarad or 5 microfarad.
Yeah, that's what I'm asking. How did you
Yeah.
determine that for your load requirements you need 22, 10, and 0.1 on the input, and 22 for and 45, 44.1 on the output? How did you determine for your load, for your current on the load, that's how much you need? How did you, what's the relationship? How did you find that value?
Okay, very good question. So basically, for linear regulator, right now you consider like this. I'll just tell you. First, thumb rules I'll tell you, and then later on I'll tell you the exact, like calculation and all. During switching regulator, we will do the calculation for C input and C output. That will be the best place. Okay. But for linear regulator, let us take like this. First of all, the C in minimum and C out minimum. That is defined by datasheet. They have told you why. Because they do not want to land your regulator into unstable state. Because the poles of those, like poles will be lying outside unit circle, and it will be unstable. Like if poles are outside, you see in the control system, it will become unstable the way it is controlled. Okay. The one more thing that they give generally, I mean, all the, let's say if you follow ROM semiconductor, they give you the C in maximum and C out maximum. Like what is the maximum capacitance that you can use, not more than that. So those values are generally up to 1000 microfarad or something. Sometimes Texas Instruments also mention their capacitance requirement that will be around 100 microfarad or something for lower grade, very low, power application. Okay. Coming back to your question, how do we decide what is the load and what will be the capacitance requirement? That depends. Let us say I'm going to choose here 3.3 volt and 300 milliampere. So based on my experience, 10 microfarad to 20 microfarad is more than enough. All right. but I have given a provision for 2 capacitor in my circuit so that one of them I can keep it DNP, okay, and one I can use it. So if there is a load requirement in future little higher, I can place this. So you have a provision of additional capacitance, a capacitor bank in the circuit, so that you do not land up in a situation where you do not have a place only on the PCB to add more capacitors. Okay, so that is a very good design practice of having extra capacitors place. Okay, but do not keep trickling about a lot of capacitors, like don't make it capacitor land land. Okay. Be very, like specific, like I want one is required, but I have put two. Don't put it 5, 6 and all because I want additional, like information or something like that. Okay. So there is no other, like other reasons. One more thing that I wanted to tell you is for
I
FPGA
think my
application.
question here was, my question was, how did you come up with, my question was, how did you know that for 300 milliamps, you need 10 micro and 20 micro? I think that's my main question. Is the calculations, is there a formula, or is it just by experience? Because I don't know how you determined
Right.
that those capacitance will be feasible for the current that you're using.
Yeah. Right now, you take it as per experience. Okay, that is first answer. Second answer is in the like yesterday I was explaining about the data sheet. There you would have seen there was like an increase in the current. Okay, sudden increase. That time there was a dip in the voltage and it was reaching like this. So this is I, which is changing from, let's say, 1 milliampere to 200 milliampere. So sudden increase will make your voltage output go transient low. Okay. So this will be also mitigated by using a higher value of capacitors. That is one thing. But the value calculation we will see in switching regulators. Here I don't have the answer. Okay. And once it goes down, the load goes down, you will see there is a spike in the output and then slowly it goes down. So basically the transients you will see in the output based on the input current, like increase or load current increase or decrease, you will see output going into transients. Okay. So try to, like understand right now that a general values of capacitors that are being used for these LDOs. Okay, so we will concentrate to like make this circuit so that you can have an understanding of like how to design circuit in the software first, and then we will see the design part again. Now again go to place, go to ground, and let us put some ground. Okay, so I'll just take one ground. It doesn't matter which ground you are taking. Okay, so anything is fine. It's up to you, like which kind of ground your symbol is choosing. Now to wire them up, you have to press W. So W is like this, and then put. If you do not remember the shortcut for wiring, you just have to go to place and wire. So this is the wire with symbol is W, like shortcut is W. So place that and it will appear. Okay. So quickly we'll just place this and let us say I'll put this one like this. Then we have this. Try to make your circuit as clean as possible. The readability is okay or not, you have to have. And along with the design, we are actually learning how to, like solve the problems which is there in the industries. Like the people want a very neat and clean circuits. Okay, so that is one thing. Now we will take, let us say the, like the part number that we will choose is fixed one. So for that we will not place any resistors divider. So fixed one, what is the part number from the data set you will come to know. So in the last pages, you will see this is the ordering guide. So in ordering guide, this is LFCSP package, and in that 3.3 volt is this one. Okay. So this part number I'll just put it. Okay. So double click this, you can put it. Okay. Or otherwise double click this whole part and you can change your parameters. Okay. Now the next thing was this adjustable pin will actually directly get connected to Vout because it is a fixed type. And enable pin I'm not going to put right now under voltage lockout. So I will connect directly. And NC pin is no connect. And I'm not going to use my power good pin. So I'll put that also no connect. No connect how to put? Either you press X so that no connect symbol will appear, or place no connect. Place there is no connect will come. Something this one no connect. So no connect will come. So this is the complete circuit that is designed. Okay, that is one part. Okay. So if you want to, do one thing, let us say you want to develop, generate this PDF for this. So what you have to do is you save this one, then you press file, and here print will come. So you can print this. So in this software, only print option is there. In actual OrCAD, there will be a PDF export. So that PDF export will be a smart PDF, which will have all these parts, like properties also intact into that PDF. So once you hover your mouse there in the PDF, it will tell you what is the capacitor, what is the package, manufacturer, everything it will tell you. Okay. But right now we'll just do a print and keep it for us. So just to print, you can just press OK and write down your file name. Okay. So let us say I'll just write test schematic. Okay. So this is the circuit that is looking. So hope now you understand, like in your like companies or somewhere you would have seen that this kind of circuit actually like are basically drawn and shown. Now let us make this little better. What did I leave? Those all things we will try to enter one by one. So very first thing that we will do is we will connect power good pin. Okay. So we want to monitor power good. So what to do for power good? We will connect this power good with a pull-up resistor. Let's say 5 volt I am going to put. So I am going to put a pull-up resistor. And I'll drive through a MOSFET because its current carrying capacity will be very less. Okay. So I'll drive a MOSFET. And this MOSFET, what will happen is whenever this is actually okay, then it will be pulled high. And in that case, this MOSFET will be turned on and my 5 volt will be flowing towards this. So my LED will not glow. It means if 3.3 volt is there, my LED is off. And what will happen is when this is having some problem like output, my power good pin is pulled low. And in that case, my MOSFET will not be working. So this 5 volt is anyway available always. So this one will make sure the LED glows. So this red indicator will tell you that my power is not okay. Understood? So this is the concept that has been put here. We will see that. If you want your LED to glow.
A question. Yeah. So P good. So I know that it's there to tell us that if the voltage is stable or not, but you see in that pin, P good, is it, I mean, what's the level of that voltage? Is it 3.3 volts or is it, I don't know. Yes. We didn't really get much explanation on that, on the P good. How much voltage comes out of that pin? That's my question.
Okay. That is very good question. So I think yesterday I had explained everything, but you were not there. Let's do that quickly. So power good pin, if you see the block diagram of the data sheet, you will see that power good pin is actually like this. Okay. This is my PG pin, and this is the, let's say, boundary of my IC. Okay. And this is connected to the ground, and here your feedback pin or something is coming, which is driving the gate. So this MOSFET is inside the IC, and this is my PG pin, which is outside the IC pin. Now, what happens is, manufacturer, we expect them that why don't you give a like voltage here, let's say 3.3 volt, so that we will just drive our PG pin. When it is not available, my PG will be 3.3, and when it is available, my PG will become 0 because it is working, right? So this is the concept, or this is the debate that is given. Now the problem that happens is, I'll tell you. Let us say you are going to drive your PG pin and to a microcontroller. So the microcontroller IO can be taking you, like, let's say 3.3 volt, or even these days 2.5 volt, or even 5 volt in automotives and all. So the logic level always changes. Understood? So it is not possible for the manufacturer to give a internal power supply for this drain. Okay, drain of the MOSFET. So that is the reason what they have told you is, I don't want to give you any voltage level here. It is your duty to pull up this guy. Okay, so whatever way you want, you pull this up. let us say I am going to pull up this PG pin by 5 volt. So what will happen when this FB pin is low? This will not be working. It means this PG pin will be pulled to 5 volt logic, and we will actually see a 5 volt high. Now similar to that, if you pull it to 3.3, then it will become 3.3 volt high. And when this goes high, then it will be start, like MOSFET will turn on, and this PG pin will be pulled low, indicating that output is low. Understood? So it is your duty to put what is the logic level you want to put, and that's why it is called as open drain.
Okay. My question is, so the feedback connects to the PG connects to the feedback pin internally. Is that
No, no, no,
essentially how
no,
it is?
no, 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 no. Let me show you the internal circuit block diagram here. See. Not shown here properly. But anyway, this PG power good pin, it is coming, okay, and it is driving a MOSFET here, okay. This is a MOSFET which is being driven. I mean, some circuits I'll show it to you, the internal circuit. So this MOSFET is being driven by this output, and if it is not okay, it will make it high, so that actually PG pin will go low because my MOSFET started working. And MOSFET turn, I mean PG pin goes low, indicating my output is not okay. And it cannot go high even if my like feedback is coming low. Why? Because there is nothing to pull up a higher voltage. That's why it was open drain. And you are supposed to put your output, voltage level from your side. That's why it is asking you that my PG pin is open drain, pull up is needed if you want to use this. And if you do not want to use this, you don't connect anything, keep it not connected. So many people do not want to monitor the output. Any output will appear, don't worry about it. Like that they say, and they do not want to waste one of the MCU pin to monitor this, or they do not want to put one LED to monitor this. Got it?
Yeah, just to understand. So if the V out is low, the P good will be high, and if the V out is high, the P good will be low. Is that
No, 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 no.
correct?
You are no, no, no. You are mistaken. What I am telling is, I am not telling about V out high or low. I am telling about V out is okay. Okay. I don't know what is V out. My V out is okay within the range of plus minus 5%. Like let's say it is going to be 95% to 105%. Okay. Then my power good will be pulled high to whatever logic level you have given the voltage here. So V out, I don't want to pull up PG because PG I cannot monitor through V out. I will put an input voltage or some other voltage, which will always be available because we are monitoring V out. So we cannot pull it to V out. This is not recommended. Anyway, so you will understand through the way, like this power good pin is very good feature. We will explain, like add more circuits towards this power good. Okay. So let's try to understand right now that you are required to pull it up in the data sheet. It tells you very clearly in the where is my pin description? Yeah, here. So in pin description, this power good pin, it tells you this is your open drain output, requires an external pull-up resistor to V in or V out. Okay, it is telling V out also not a problem. But if this part, if the part is in shutdown, current limit, thermal shutdown, or falls below 90% of the nominal output voltage, PG immediately transition low. It means like if the IC is in shutdown condition, or there is a problem with current limit and all, or thermal shutdown, like it has heated up like anything and thermally it is shut down, or falls below 90%, they have programmed it. Okay. So the PG pin, you can actually program it by yourself also in very good ICs. Like you want 90% lesser, then you give a red signal, or you want 95% and then give a red signal. So it's up to you, like how much below you want. And then PG immediately transition to low. If the power good function is not used, you can leave this pin unconnected or connect it to ground if you do not want to use this. Understood? So if there is a problem, it will transition to low. And if there is no problem, you have pulled it high, so it will be telling you high.
Okay, because I know that it's based on MOSFET. So if the I know that MOSFETs, if the gate, if GS is low, that means the drain will be high.
Yes.
So does that mean in PG? So that means in PG, if it falls below 90%, that means the PG will be high. Correct?
Yeah, because FB pin is not indicating that you you short circuit the MOSFET. Like it is not turning on the MOSFET.
Okay, yeah. So basically, if it goes below 90%, your P good will be high. So that means your LED will turn on. In that case, if you have an LED.
No. Wait, Jonathan, you are getting confused. Wait a moment. Very simple thing you understand about this PG function. Okay. First of all, this MOSFET is inside the IC. I don't have a control on the MOSFET. Okay. This FB pin tells based on the output, not this 3.3. Okay. The output of the IC. Okay. Now let us say V output is not okay. Understood? Then what will happen is my FB pin will go high, indicating turning on the MOSFET. So once it turns on the MOSFET, it will get short circuited. So once short circuit happens, like once actually the MOSFET turns on, my drain pin, this drain pin will actually pull the PG pin low. Understood? So V out not okay, my PG transition to low. Okay. When my V out is okay, just consider it is okay, more than 90%, they have programmed it. If it is okay, the FB pin will go low, making sure that MOSFET does not turn on. Okay. And if the MOSFET is not turned on, the power that is connected here, logic level to PG pin, do you see any way it will go ground? Because it is not turned on. So there is no path to go to ground. It means my PG pin is directly taking 3.3. So it is high. If it is high, indicating my Vout is okay. All right. So you just consider this one. Don't consider about LED. LED, what is happening? It's up to your control. Whether you want, okay, that I'll tell you a little later. First, you understand if PG is high, my output is okay. If PG is low, my output is not okay. Understood?
I mean, I get it, but
Leave that LED
I'm just
part.
trying to understand.
LED part, I'll tell you little
I'm just
later.
trying to understand. Yeah, I'm just trying to understand the feedback. So if FB is coming out of, let's look at here. So FB is coming from the yeah. So FB is coming from the internal. So if
Internal
feedback,
circuit. No,
yes,
don't,
okay. So if
one more thing. Don't consider this FB as the feedback or adjustable pin, this one, okay? There is internal circuit something which I am just telling you some feedback is coming to turn on the MOSFET or turn off the MOSFET, okay? Not this thing, okay?
yeah. So if feedback is high, feel good is low.
Yeah, because it turned on.
Yeah. If feedback is low, feel good is high.
Because it is not turned on.
Yeah. Okay, that makes
That's
sense.
all.
Thank you.
That's all.
Yeah.
Now it is
Makes
your
sense.
duty. It is your duty that when my output is okay, you want to turn on your LED or you want to turn off your LED. Understood? It's
Yeah.
your duty. I don't care like how do you want to make your
Yeah.
circuit. Okay.
Yeah. So the feedback you show there is not the feedback that we have outside. It's not the same.
No. This is internal
Okay.
circuit. Actually now
Okay. Yeah.
better I'll show you one page. Is that open? Like very good
Because
circuits
I
are
thought
there.
I thought the feel good has the same feedback as the V out.
No. Mhm. Actually, I don't want to introduce little complex linear regulators because I wanted to teach you guys little smaller one, and then I want you to go to the what is that? Some RF application, very ultra low noise LDOs. Okay, these are very costly, but they are very useful. So, so if you see like RF application like VCCO mixtures, LNA, so all these things they are very, like utilized, or even military applications and all. So in this one, if you see the PG pin, like we are talking about. So this PG pin, how power good pin works, they have very clearly told you. Okay. So let me see the block diagram of this. This is 50-page data sheet, so it has given you a lot of information, and I want you guys to design a project on this. Okay, so we will do that once we complete this. Okay, so let us talk about PGP. See here what is happening. My PG pin is this one. Just forget right now that this PGFB pin and all these things, let us say these all are not there. Okay, so only this is there where PGP. So PGP will go high or low based on your, like putting the higher voltage 3V3 or something, and then you connect it to your PGP here. That's it. Now, what is going to happen? See, there is a voltage reference that is there here, and there is some feedback that is coming here, which will make this guy either low or high. Understood? So this comparator will make sure that the gate of this MOSFET gets a high or low based on the reference and this input pin. And this input pin is actually coming from internally, like output side, it will be coming right now here. Here right now it is coming output side. Okay, but in that case it was internal. So there, that is the thing. This MOSFET will turn on or off based on the comparator output. So I am telling this as feedback pin. Here feedback is coming, and then this is decision is happening. Then output is coming as a feedback to the MOSFET. Okay. So just consider like this, a complete, like what is that? A procedure. So hope you are clear about this PG pin right now. Okay. But one thing consider that PG pin is open drain type. So you need an external voltage labels. And what is the voltage level you want? You decide it. These days, semiconductor industries actually uses 24-volt logic level. So 24-volt logic level, they will not give you internally. Understood? From where they will get 24-volt. So it is your duty to connect here 24-volt. Some people use plus minus 15-volt logic level. So we will use plus 15-volt also. Some people use 6-volt. Some people use 5-volt. So it is very varying. Like it is not common in all the industries. So I work in semiconductor, and there we use 24-volt. You would not have thought of like 24-volt logic level, is it? Yes, it is. Understood? So this is how it works. All right. So while creating this circuit, we will try to utilize this PG logic label, let's say 5-volt. Now I'll just create a simple circuit and ask you guys only to create. Okay. So let us say I'll just put a MOSFET. So I'm going to put a MOSFET, and then I'm going to drive through a resistor and all. Okay. So let us put one resistor, 0603 I'll put. And then I'll put one pull-up resistor also. See, this is a gate, so you don't think that a gate is pulled up. This PG pin is pulled up. There is no place. That's why I'm putting it here. Okay. And what else? That's all. So we need one LED. So let us, I have the LED as well, so I'll use them. Okay. Now we'll need a ground, and we'll need ground here also, and we need power. Okay. So now let us connect. While connecting, we just have to make sure it is properly connected, and this will also require pull-up resistor. So pull-up, I'm making it 5-volt. Okay. I was expecting some other questions from you guys. Okay. That's all. Now they tell you that pull-up must be with some resistor. So like right now, I'm going to keep, let's say 10 kilo ohm. They would have recommended like it should be 10 kilo ohm to 100 kilo ohm or something like that. So don't keep very high value, just keep it like a normal value. So this is one. Another thing is I'm going to connect this line to this PG pin. Okay. So I can name it. Okay. So right click it and put a name. So instead of right clicking, you can just press N for net aliases. So that is called net aliases. N. So aliases. Okay. So I am going to write P good. So this P good, and the same, if you want, you can select this net section and control it and put it like this. Okay. So that way you can put it. This extra part you can delete it. Okay, the name has been deleted. I'll just press N again and P good. So this P good is actually connected here. Okay. Now if you want, you can do all other calculation. Like generally LEDs are having 1.9 volt drop. Okay. So what will happen? What will happen? There is that 1.9 volt drop is there. So basically the current that will be flowing, let's say I have a 2 milliampere current rating LED. So I'll have I LED will be how much? 5 minus 2 volt, or let's say 1.9 volt I am telling. So 1.9 volt divided by 2.21 kilo ohm. Okay. So that will be how much? Around 3 by 2. So 1.5 milliampere or something. Not exact calculation, but around that. So that is the reason this 2.21 kilo ohm is used. If you want to increase the current, you have to reduce this resistance R9. Okay. That is what. So, so you can just put it like this, 2.21 kilo ohm. Okay. That's all done. So this was all about this. Now let us do the more design into this circuit. So sometimes what happens is our input voltage might go beyond the limit of 5 volt. So we do not want our IC to like get more than, let's say, 6 volt or 7 volt. So what shall we do? We should limit the voltage or clamp the voltage. So that's why we try to put a clamp, like what is that, TVS diode or something. So we will put a TVS diode here to clamp it or to avoid the transient. So let's say this 5 volt is getting a transient. So this transient, already, like it goes up to around 1 kilovolt or more than that for few microsecond, let's say 5 microsecond pulse or something. So I don't want to, like have those problems. So I can use a TVS diode here. So let us say I make that also. So I'll put TVS. I'll take unidirectional. Okay, so TVS diode is put. If you want, you can specify your voltage level. So how much shall I put? I'll just put 6 volt. Okay, I've just written 6. That is more than enough to indicate a 6 volt TVS diode I have used. Same thing, if you want to utilize at the output also to limit the output voltage to 3.5 volt or something like that, you can use a TVS diode this side also of how much. Let's say I want to use, don't want to go 3.8 or more. So let's say 3.8 volt I want to limit it. So that way you have protected your voltage levels at the input as well as at the output. So this is voltage clamping. Now the output current was 300 milliampere. So I don't want my input to take more than 300 milliampere, because sometimes what happens now, this IC capability is 500. So people just load it more than 300, but I have not designed it for 500. So I will limit that. So how to limit that? I can put a fuse also. Okay. So before giving these two input, I'll put a fuse. So just type a fuse here. If your fuse and all these things are available, then only you will be able to use, otherwise you won't be. Okay. Now I have just put a fuse. It's your choice, like which part you are going to use. That's why part selection is important. Okay. So right now I am going to make it, like 500 milliampere. So the part which is chosen is actually 500 milliampere. I'll just delete that or let it be 500. It's up to us, like how to do that. So more than 500 it should not take. Okay. Now let us say we want little bit filtering also. Like I don't want a noisy output at the output side. So how to do that? We can utilize some ferrite beads. Okay. So that ferrite bead will, like remove the noises. So I'll just go and put ferrite bead. Or FB is there. Yeah, FB is there. So that ferrite bead will remove the noises. Now this 220 is actually indicated 220 is actually indicated the
Sir, what is the
resistance.
difference between inductor and ferrite bit? Is there any?
Yeah, ferrite beads are actually the filters, and they are very low current carrying capacities. Okay, inductors are storage elements. Okay, magnetic elements. Ferrite beads is also magnetic element, but their response is resistance wise. Their resistance increases at very high frequency. Let's say at 100 megahertz. If you see this particular ferrite bead at 100 megahertz, its impedance will be 220 megahertz. Okay, 220 ohm. Like if I tell you how to select a ferrite bead, let me just give you an example. See, so ferrite beads, this looks just like resistor, capacitor and all. So same way manufacturer and all will be there. But right now, like these are like filter types like power line filtering or signal line filtering. So power line little bit higher current, signal line little bit lower current. Okay. The only thing that you have to actually see is the impedance at a frequency. Okay. So let's say 220 ohm I am telling at 100 megahertz or 470 ohm at 100 megahertz. Basically those are used in ADC lines. Okay. You do not want your like your signal to couple into the ADC pins. When I will teach you the microcontroller circuit design, that time I will tell you. Now here this typical impedance characteristic, if you see, I am going to talk about, let's say, resistance, pure resistance. Okay, so this pure resistance below 10 megahertz, it is almost nothing, like almost 0 ohm, okay, or 1 ohm. So you see, like there is no ohm. It means the drop across the ferrite bead will be almost 0 volt. So whatever 3.3 you had generated here, the same thing will be almost there. Okay, like milliohm or something will be there, but that will not like cause any problem. Okay, that is one thing. Now, why we are putting this ferrite bead is when my load becomes inductive. Okay, so when it is inductive, then it starts resonating or something like that, or maybe high frequency load comes up. At that time, this starts oscillating. Okay, so to stop that, why I want to stop this? Because some of the loads are pure DC and some of the load is going to like introduce noise or going to cause my LDO to go unstable. So we want to prevent that. So for that, this resistance will increase like anything. It means output will not be there. So this load will not be driven because of high resistance value. So you can see with frequency change, my resistance is changing. Okay. And similar to that, other parts parameters are there like current rating, what is the DC resistance. So see, DC resistance is 20 milliohm or 50 milliohm, something like that. Some examples are I have put it. Okay. So this much ohm will be there at the DC value. Then we have ratings like AEC ratings will be there, operating temperature will be there. Package size, same size, like all the resistor size, it is available. So few examples also I have taken. So I'll upload these data sheets in these scenarios so that you can have an understanding like how it works. And derating curve also, if you see, let us say one of the data sheet I have taken this one. In this one, if you see, this is Worth Electronics ferrite bead. So in this one, if you see, you have 100% current rating up to 85 degrees centigrade or something. And after that, as temperature increases, my like my current rating decreases like anything. Okay, so this is the problem with the ferrite beads. Similar to that, other ferrite beads are there, like you can see Murata. So Murata, you have very good options of ferrite beads. So like let us say you have current rating up to 0.9 ampere to 3 ampere or even 20 amperes. So these are the series that is there available with you. The package is available with you 0402, 0603, okay, 1206. So generally in power line, try to utilize 0805 or 1206. In signal line, you can go ahead with lower package, but don't use power line in these packages. Power line, go ahead with little bigger package, okay? Because they have little better capabilities. And actual circuit of this ferrite bead is this is an inductor come a resistor in the series, okay? Okay, so this was all about the, a complete circuit design of this particular regulator that I wanted to teach you. And if you guys want the, what is that? The adjustable version. So let us say I don't want to use power good and I want to utilize adjustable version. So I'll have to put a, what is that? In the adjustable version, we have for 3.3, we have 103 kilo ohm and 60.4 kilo ohm. So these two resistor you have to utilize. So what we will do is we will take resistor I was telling you guys to ask one question, but you guys didn't ask. Anyway, I'll tell you. Or how shall I connect it? So circuit making is actually an art. Like it's up to you guys. Like how do you guys make the circuit? So try to make a beautiful circuit so that it is understandable later on. Okay. Yes. And then what was the value? 60.4 kilo ohm and 103 kilo ohm. Don't worry about the values. You can always calculate from the Excel sheet that I have shared you for any output you want to utilize. And PGP now I'll just keep it not connected. Now, one more thing you would like to see is test points, because test point is must, like what is the voltage level at this point. So instead of probing on the pins, you can probe on the test point. So you can search for test point also, that is TP. So I'll just put TPs. Let's say one TP I'll put it here, one for ground. One more I'll put it at here. One more for ground I'll put it this side also. And one more for this one more for this one. Don't think right now, like in this sheet, it will tell you that this 5 volt and this 5 volt are sorted. This 3.3 and this 3.3 are sorted. Okay. But just consider yourself that this is a separate circuit and this is a separate circuit. Understood? Just for the understanding, I'm just making it here itself. But that is the way it should be treated. Okay. And this I can delete, let's say, because one ground is more than enough for me. And these two are. Now to make it bigger or smaller, you have mouse wheel. Okay, so wheel, if you control wheel outward or inward is smaller, outward is bigger. Okay, so like that, control and then wheel rotation. So this is how zoom in and zoom out. Okay. Now if you save it and then just print your circuit, that's all. So this was the complete understanding of the OrCAD. I wanted to teach you guys the bill of materials, but that we can take up later. Okay. I'm just putting this. Okay. So in the circuit design, like circuit entry, actually not design, circuit entry, you guys have any question still? Like how do we import the library? Then how do we place all the components, wire it, print it, everything we have done, right? Quickly, if you want to see, just select the circuit, okay, or select the DSL file and go to tools. And this is the bill of material, okay? So once you press bill of material, it tells you the header and it tells you the combined property. It means like you have the items and you have in braces, there will be item. then /t, another property you can put. So this header you can put anything, but corresponding to that, this would be actual property in the components. Let's say here, if you want to find out this manufacturer, then you have to write down manufacturer exactly same spelling. Okay. Otherwise it won't come. Understood? So let us take the bill of material little later on. However, this much. Okay.
Sir, I installed this in one PC, one laptop. Can I use the same ID and password and install in one more, or is there any restriction?
I think you can use you can use that as long as you have the software with you. You will be able to use that.
Is there any device restriction? Number of device restriction with the email?
No. Actually, you have the key, so you can put the same key into that also.
Okay.
Actually, TI restricts to download the software itself. Okay. So once it is downloaded, you can utilize in many.
Okay.
Yeah.
And as I told, Excel sheet you shared, where you shared, sir? The work drive link, so OneDrive link?
Yeah, OneDrive link, everything is shared. So let me just show it to you guys if it is there or not. I think I have shared you all the files. Okay. So I'll see and send you guys. Or I think you have or not. I don't know. Let me just do one thing first.